Hello, everyone. Before we start, we'd like to introduce our developers. So we're the Google Developer Student Club, and we're offered by Google developers to support community-run developer groups. And of course, we're sponsored by Google. Yay. And for our future events, we will be holding Chronicle, which is our flagship annual hackathon. And we'll have GDSC, which are workshops related to Google technology. And we'll have IB8, which are tech talks, panels, and network events. And today we're bringing to you this workshop together with MISC.
Yeah, sure. Yeah, with me and Amy from the MISC Club, Melbourne Information Security Club, and we run kind of like weekly workshops on security-related topics and try to keep them hands-on. Events, yeah. Some upcoming events we've got Industry night, yeah.
We're doing like a mini golf event with at home.
Yeah, so that should be more details about that coming out soon. But we'll hopefully be able to see some of you guys there.
And we have weekly workshops.
Yeah, we try to do a workshop every week. And so we always post it on our Facebook page. I guess we'll start off with just kind of introducing Leetcode, what it is, and then we'll hand over to the Google Club, who's going to run us through some examples. So I guess, I mean, probably most people know here, but Leetcode, I guess, is just like an environment where you can practice programming, your programming skills, and specifically interview questions. You can usually select from a range of different programming languages to use, so pick one that's comfortable with you. And it's really based on problem solving and showing your methodology. I guess I thought I'd kind of briefly go over as well some of the things you might see in technical assessments that might not be like the Leetcode's one as well as others. So I guess you might see instances where you kind of just sent a link to fill out complete technical assessment given a certain number of questions in a given time, and then you complete that, and then they'll kind of review it after the fact. You may also have a live programming interview where you're in person or remotely having an interview, and then you have to go through some questions with them there. And another thing I thought I might mention is also you can have technical questions that aren't programming related necessarily. One common one you might see something like this, explain what happens when you type google.com in your browser. And at first glance it might seem like quite a simple question, but you can, they might be looking for you to go into a lot of detail about some of the technologies that actually let you access information on the internet. And I guess the reason we do technical assessments, or why we practice for them, is because they let you demonstrate your technical skills to an employer. And I feel they're often more worried about more looking at your approach to solving an issue and how you solve it, rather than just if you get the if it's its correctness, or if you get the answer question, and you get to show off some of your efficient modular readable code, which I'm not an expert on, which is why we've got these guys here. They should be able to help us out. Next.
So we want to talk a little bit about algorithms and data structures, because they're kind of the foundations of programming, so they'll really help you with your code question. So what is an algorithm? So an algorithm is the steps it takes for a program to complete a task. Every algorithm has a clearly defined problem statement, input and output. So every algorithm is specific to a certain task. They will have a clear order. Each step must be explicitly clear, distinct, cannot be broken down further, and every algorithm must produce its own results. Measuring algorithms. So algorithms can be measured on their efficiency and correctness. So correctness is, does the algorithm produce the desired result? And efficiency is how much time it takes and how much space, how much memory the algorithm takes within a program. We measure time complexity. We often consider the worst case scenario to be aware of how much time it could take. So some of you may be familiar, but we measure time complexity with big O notation.
We'll go through the details of big O notation in a few slides. So don't worry if you don't know.
What is a data structure? So data structures are how the data is stored in programs. It's the collection of values and the format that they are stored in, the relationship between the values and the collection, as well as what is expected in the structure. So data structures to be able to complete this following operations. To be able to read and access values in the data structure, search for arbitrary values, insert values at any point into the structure, and delete values in the structure. We can measure the efficiency of a data structure by comparing the big O notation for the following operations above. For example, in an array, the big O is O of n to find the value, and it's log n for a binary search tree. But some common data structures. So we have an array, which is just a collection of elements that are stored contiguously. Basically means they're stored in adjacent memory locations. And it can be indexed, and it doesn't necessarily have to be stored. And we also have a binary search tree. So that is an ordered and sorted binary tree where the left subtree of a node contains only nodes with keys lesser than the node's key, and the right subtree contains only nodes with greater than the node's key, and all the subtrees are also binary search trees.
And I'll just go through an example with arrays and binary search trees. Hopefully this works. Oh. All right, so let's say we were trying to look for the number 7 in an unsorted array, right? To look for the 7, we would do an algorithm. Oh, sorry. Okay. All right, there we go. All right, let's say we were looking for the number 7 here in the unsorted array. We intuitively know that it's at the very end, but the algorithm doesn't know. We need to create a way in which we can traverse this unsorted array, and we use a simple algorithm called linear search. So with linear search, we pretty much check every single possibility. We start at 3 and we keep traversing over until we find the 7. And we call the size of this array n, which stands for the number of nodes or the number of values within this array. And because we have to look through every single one, we call this linear search O of n. However, if we have a balanced binary tree where everything on the right, for example, if we're looking for a 7 here, right, we would first compare it with this 4 value. But however, we know that 7 is of course greater than 4, so we can pretty much delete the whole left side of the tree because we know the 7 isn't there. So from there, we can traverse downwards to the 6. And from the 6, we repeat the same idea. We know that 7 is greater than 6 and that it can't be on the left side. So we traverse again and we found a 7. So instead of like the unsorted array of looking through every single element, we create this data structure which has a predefined set of rules. But we utilize these rules to traverse and be able to find the 7 number and not O n time, but we find it in O log n time, which is much more efficient. For example, if we had like 1 million numbers in an array, for example, it would take 1 million queries in the worst case scenario. However, in the balanced search tree, it'd be log 1 million instead. So that's why we have these data structures to create sort of paths for ourselves. And we follow these rules to search and insert and delete in a much more efficient way. And we'll head into some examples. So if everyone wants to head on their laptops and go into leetcode.com, you can go ahead, make an account and search up the question 217 contains duplicate. So this is the interactive part of the workshop in which everyone gets to try, because the best way to learn Leetcode is by doing and not by listening. Yeah. I'll take it from here.
Yeah, don't take it from there.
Okay, sure.
Just if I go with time, if you
Mhm,
feel
mhm,
fine, I
mhm.
can stuff the end up like.
Okay. Okay, sure, yeah. Oh no, I'll be okay, I think. It's so annoying because how do I do this? Hi, sorry, just one more thing. Does anyone here not know what a set? Well, sorry, what a stack or queue is? Anyone not know? Just raise your hand. Please don't be shy. Okay, and what about set or map? Sorry, just seeing if I need to explain what those are. Does everyone know what a set or map is? Okay, yeah. Yeah, so just go ahead and we'll reassess in around 5 minutes. I can explain what some of these are. Hi, so we're just quickly gonna go over this contains duplicate answer, and I'll walk you guys through it. So for a list here with 4 elements, we intuitively know 1 and 4. Oh, sorry, 1 is the same number and it pairs twice, right? So if we were to take this first one, right, and then compare against the 2, and then the next one, and then the next one, we would see that there would be a duplicate. And through this approach of using 2 for loops, we compare every element with every other element. For example, we compare 1 with every other one here. And then let's say this was let me change the question. Let's say we compare 1 against every other number in the array, and we know that there isn't a 1. We can then move on to the 2. And then we can compare every other element with the 2. This solution would take O(n) squared, because for every element here, right, we have to do n checks along every other single element. Oh, take O of n squared. However, we can use something called a set. So in this set, I'm just going to draw over here as a table. Through a set, we can check whether or not this element has already been seen, and we can solve this problem by passing through this array only once. For example, let's say we start at 1 here. We check if 1 is in the set. We know that it isn't, so we add it to the set and we just add a 1 here. All right, and now let's move on to the 2. There is not a 2 in the set, so we append a 2, and then we shift the pointer across. We check for 3, etc., until we end up here. When we check for the 3 and whether it's in the set, we see that it is already found. And from there, we can return true, and we return false if we reach the end of the array and we have not found any duplicates. By using a set, also known as a hash set, we can look up in O(1) time whether or not an element is within the set. So instead of comparing one number with every other number, we can check it directly if it's already been saved in memory. So through this solution, we can achieve a time complexity of O of n by only having 1 pass through. And back. So just to reiterate, the first approach was brute forcing, and the second approach was using a hash set. And here is the Python implementation of using a hash set. We declared a hash set as an empty set, and we iterate over the numbers, checking if it's in the hash set. If it is in the hash set, we return true. If it's not, then we append it to the hash set, and then we keep repeating for every number. And at the end, if we've gone through every number in the list, we return false. And here's the next question. Question is called number 1 to sum. So okay, we'll start with 4, right? When we have a 4, what are we looking for in the rest of the array?
Looking for 9 minus 4.
Yeah, we know we want to sum to 9, so we find the complements, which is 9 minus 4, which is 5.
Yeah.
And we look through 5 and go. So,
And if 5 is not in the hash set, you add 4 to the hash.
yeah.
Okay.
Wait, what did the okay, they look for the complements. Okay.
Yeah.
All right, we're just gonna go through the answers for this question. If I could get everyone's attention, please. So for this question, to sum, we want to find a pair of numbers which sum to the target, and we want to return the indices of these numbers. So for example, we're starting at 4. We want to find the complements which would sum to 9, so we will look for 5. So once we're at 4, we want to look for 5, checking every single one. But however, like previously, this would be inefficient and would lead to a brute force solution of O in squared time. However, we want to solve better than this. So we can use a data structure called a hash map. So in a hash map, we link a key with a value. And the value and key pair that we want to link here is the complement and the index, because we want to return the index when the question is solved. So in this hash map, we would find the complements and the index. So for example, with 4, we're trying to look for 5. And because we cannot find a 5, we add it to the hash map. So we add the difference here, 9 minus 4 is 5. We add a 5 here, and we know that this would be at the 0th index. All right, let's move on to 3. We know the complement would be 9 minus 3, which is 6. 6 is not in the hash map, so then we add it to the hash map, which would be 6, and then 3 would be at an index of 1. And we keep moving forward to the 2. We want to find the complement 9 minus 2, which is 7. We check the hash map. It is not there. We add the complement and the index. We move on to 7. We find if we find if 7 was in the hash map, so we know a complement already exists. We've already traversed and we've already found a complement. So we know we've already found 7. That's great. We found 7. We also know the index of 7 already here, which is 3, as well as referring to the index of 2 here in the hash map. So our result for this question, we would return 2 and 3. Okay. So just to code the solution up. So we want to initialize a hash map. And in this hash map, we want to store the complements as well as the index. And now we want to iterate over these numbers. So so the for loop would iterate over. Is this too small? Is this okay? Okay. We would want to iterate over the numbers. And we would calculate the complements. And we would check if this complement is in the map. If diff and previous map. And if we know this complement is already in the previous map and that we've already seen it, we would just simply return the answer by indexing into this dictionary. Oh, yeah, they wrote. And if we have not found this in the dictionary, we then append our current answer to the dictionary, which would be previous map. And oh, whoops. Yep. And if we run the code, remember the truth, please work. Oh no. Oh wait, whoops. Bro, what's going on? Wait, and it's not defined. I chose it. All right, now I'm here. All right, there we go. Yep. And we can go back to this. So the intuitive answer is the brute force checking every single possibility, but through a hash map and keeping track of the difference and storing it in the hash map with a key complement pair, we're able to solve the problem in an O(n) time with one single pass through. And here's the next question. Feel free to use the library methods to help you in this question, by the way. Okay. Okay, yeah, sure. So do you understand what a hash map is?
Is it like the initial list where you like store your values?
Okay, sort of. Sorry, I'm doing a whiteboard here.